Much, Maria, for this introduction. For a moment, I wasn't sure who you were talking about, but in any case, got it about recording. Thank you very much for inviting me. I feel the fact that my understanding was that the students chose and that they chose me. The CV doesn't play any role here. It is a great honor to be chosen by the students. It's another award that you don't put it on CVs, but honestly, the relationship when students appreciate in such a way what you can give or what you have given, it's personally, I don't think there is any great honor or award that I could have. So thank you very much for all of you. And of course, for Georgia and Maria and everyone else who was involved in the organization. I tried to, since it is a general topic of the workshop and a general an audience from a general graduate program or undergraduate undergraduate students as well. I tried to come up with something that would make sense, would not go deep, would not go very deep into something that will give a flavor of some aspects of data management from the dungeons in the 10th basement all the way to applications that are not related, are seemingly not related. So we'll see if I succeeded in this. So let me begin. I have, unfortunately, the way it was all structured to achieve this, I have way too many slides. Could you tell me exactly how much? I have 1 hour, including questions, right? So I'll move according to this, and maybe we won't see one of the corners, or maybe we'll just open the door and then close it quickly. So
basement, maybe you can leave the basement and just go to the penthouse directly.
Well, you'll see. We'll see. We can do it personalized. You know, you can express opinions at some point, and then you can recommend. So let me share my screen first of all. Do you see my screen? And now do you see
yes.
it full?
Yes.
Full screen. Okay. So you had the title and my name and my two affiliations. The semicircle in the bottom is the name of the group that a bunch of us faculty at the university, most of us affiliated with Athena as well in one way or another, have established, and it's our home within the homes that we have for the management of data, information, and knowledge, and everything that goes with it. So I will start from the penthouse and just say, you know, the penthouse is the best room in the building. So that's where I will start. I mean, what do I want? First of all, I want slides to change. So I want to build an adaptive storytelling, story experiencing to a system for people to be able to engage with information, with knowledge, with environment through stories. The stories that they are not just narrations, they experienced in them. And this effort has had various names. And if you look at the architecture, the plan for the penthouse, you see very colorful, very beautifully arranged and so on. You write stories on the left. You have the the playing of the stories that give you the experience, the storytelling engine, interaction engine, and the mobile web, and so on and so forth. And it has, since you want it to be adaptive, not everyone has the same experience, you want it to be adaptive. You want to have an adaptation, a recommendation engine on what story, what experience to have, or how an experience can evolve. So each one of these boxes, but certainly this one, let me have my laser pointer. Can you see my laser pointer? I'm moving it randomly.
Yes.
Yeah.
Okay, great. Thank you. Okay. So most of these boxes are individual presentations, but this is a huge piece of software. So essentially, we need something like this, which has many pieces. And so the penthouse on some lower floor, it depends on an engine like this. So what is the architecture of the lower floor that is a recommender system? Paros is the name, profiling attitudes for recommending, and so on and so forth. Well, it has a whole bunch of pieces where you observe the behavior of people and environments, and then you profile them, and you come up with user models and profiles. And then on particular applications like the storytelling, story experiencing engine, you select the right profile for the user that comes to this. And you need a lot of information, both on the models, on the observations, on external information to feed into adapting or recommending stories or parts of the stories. So you need information systems. By the way, every picture that I showed you has existed for many, many years. I didn't create it for that, for this presentation. So it is true. It's not a fictitious thing. So you see information systems. So you need an information system there, a data management system there, which is something like this. So let's go further down in the floors. You see, by the way, when you're in the penthouse, everything was colorful and so on and so forth, more artistic, more beautiful. As you go in lower floors, it becomes gray and darker, and because there's less light. So, come on. Why is it not moving? Okay, so what is in the lower floor? There is a database management system. So what is the architecture of that? And this is one of the pictures that you can see, that you can find, that capture a database management system. I won't go through all the pieces, but there's lots of rooms and lots of stuff. And recommender systems and stories and so on are graphs. And there are approaches to recommendation that are graphs. So when it comes to query optimization and planning executor, you need to do some optimizing and processing on graphs. So, yeah, okay, fine. And also, there's a lot of text in stories. There is a lot of text in recommendations that you want to use, for example, reviews and so on and so forth, or text that give you information for what you are to recommend in order to write the story. Stories have scripts. So how do you store strings? How do you store text? So when it comes to access methods, the true dungeon, you can have string columns in your data, and how do you compress them? How do you store them efficiently? And then because you have graphs, when you optimize, when you process, you need to deal with graphs. So even further down from this data management system, truly in the dungeons, there are lower level technical challenges, lower level rooms that together with others, of course, support some of the floors above, which support the ones above, eventually the penthouse. So I wanted a penthouse, I want a penthouse, and in order to do it, I show you some of the rooms in the lower floors that I need to do that. So that was the top down, Maria, the requirements, the needs. And now I'll go into the details. I want to enter, of course, in all the rooms of all the floors that I showed you. But I'll end and I'll give you a glimpse of the 4 floors that I focused on, starting from these 2. By the way, unless Maria, you say otherwise, people can interrupt me with questions, or we can leave all to the end, whatever you want. It will be done. That will be done. So
whatever you'd like. There is a raise hand feature under reactions. Sorry, there's a lot of
I don't see
here.
I don't see that, Maria, because I'm in full
Yes.
screen. So if you see this, then you interrupt me.
Okay.
Okay, good. So these are in abstraction at different layers, the 4 engines that will have a sneak peek into some of the work that is being done within Magic across the University of Athens and Athena Research Center. So we'll start from string compression, adaptive compression for scans on string columns. And Yannis Foufoulas is the king here, with a pair of Lefterises helping or having helped in the process. And Yannis is finishing his speech now. So what are the challenges when you have string columns and you want to process them? You have to make sure when you transfer data to be low and the processing cost to be low. We will focus on reducing the size, which helps both, but also laying it out appropriately that may help them processing the cost in a compressed fashion. I want to emphasize again that I will not be going into too many details, but I'll give you some flavor of some of the details. So strings have been traditionally stored as dictionaries because strings may be long words, long phrases, larger text, lots of repetition. So usually you use dictionaries. So if the raw data, and here, for example, we have a bunch of names and in blocks on disk, you have to store in a column these names. You don't store them like this because John takes a lot, James and all, even longer names and text take that. And there have been 2 approaches. One has a global dictionary, where you take all the values, you store them in one place. And then the offsets that they have, the way they are stored, you only store those. So John, which is the first one, so it is in place 0, you don't store John a lot of times, but you store 0 here, and so on and so forth. You save a lot of space. And there is the other option of local dictionaries, which says, no, you keep the block structure, and you do this within the block. So you find the values that you have in one block, you store them once, and then you have local offsets in this little dictionary. And in the second block, then again, a local dictionary and so on and so forth. This is the way that things have been. And here things are sorted because it helps with some processing. Let's ignore that. So when it comes to querying, for random access, when you're looking for a particular one, the local one is best. For scanning, the global one is best because you scan directly and you have only one place where you find a value. When it comes to compression, the size, the local one helps with the offsets. There are fewer offsets, smaller offsets, because it's only up to whatever fits in a block. The values, though, are stored more time. So in terms of compression, the global one helps. And with respect to the data and how during processing, what is happening, whether you can store things in memory or have high cardinality, a local one helps. And one of them is more for transaction processing. The other one is for analytical processing. So Yannis and company, in this one, we say, okay, let's have differential dictionaries. Let's try to have the best of both worlds. So if local and global and local are like that, the differential dictionary starts and has the first block the same way, nothing changes. But then you take a differential between what comes in the next block and what you've already stored here, you find the differences and you only store things here. And then for the values, you use the offsets of the previous dictionary as well, of the previous block, and so on and so forth. And then at the end, the only difference is Mark and Philip here. In the end, after a fixed number of differential dictionaries, you start again with a local one. But this is not good enough because data change, the distribution change, and so on and so forth. So why fix the size of every string of one local and a bunch of differential, and don't do it adaptively based on the data, and sometimes even based on the users that they have? So you have the first differential, the data is a little bit different here in order to fit the example. You do the first sequence, and then at some point you decide and change, and you do a second differential sequence, a local and the differential, and then at some appropriate time, you change and you have adaptively another one. And the decision is made at any point. What do I do? Do I do another differential, or do I start another sequence with a new local? And there's a rather complicated cost function with prediction and based on what we've seen so far and so on and so forth that captures this what to be done next. And the trick, of course, is to have it doesn't move. I'm not sure why it's not moving. Okay. And now if we can compare the dictionary comparison, in all elements, the differential dictionaries themselves help with the querying for both OLTP and OLAP. And if you make them even adaptive, then they help with everything else. And although it may seem that scanning or joining or sorting, range scans become a little bit more expensive, and this is accurate, the wins on all the other elements are significant. I won't show you the algorithms. I just want to show an evaluation. Why is it stalling? Okay, so we run the typical synthetic and real data experiments, synthetic based on Microsoft Academic Graph, which is a huge graph with many strings like titles of papers and conferences and so on and so forth, and both uniform and zip distributions, sorting the data or having randomly and so on and so forth. Huge graph, as I said, and just to get a glimpse of the performance. First of all, the file size, the adaptive is the blue, and you see it's never worse than anything, and often it's better than any other choice, and it adapts very well. I really don't know what the problem is, and you can see everyone is either at that level or above. When you scan randomly with a filter, then again, this is the adaptive one. The color coding is problematic here. And again, in all cases, SQ increases. Still, it is the most adaptive of all cases. And random access, you're looking for one value. Again, it is the winner overall by having this adaptive differential dictionaries. So that's how strings are to be stored. And there is, since this paper appeared earlier this year, there seems to be some interest from some industrial labs looking to further to see if something like this may make sense to change in the real systems. So that's one room, a breather, If there is a burning question, Maria, then I can take it. Otherwise, I'll move up a little bit.
No, not yet. So you can
Okay.
continue.
All right. Thank you. Now, graph processing, and in particular, the two-hop. I'll explain this neighborhood computation in interactive graphs. And Manos is another PhD student of mine towards the finish line of his PhD. So let me give you by example what the two-hop neighborhood problem is. You have a graph, G like this, it's very simple. And what you want is, it's directed. And what you want is to find the edges show nodes that are of distance 1. How about nodes that are of distance 2? So S1 with T1 through this path, S2 with T2 through this path, and so on. So this is what you want to get, the G2, the two-hop. And usually it's not just reachability that you want, but you may want also some aggregate on the paths that show you, that give you the ways in which the nodes are distance 2. So here we can have just a count. And so S1 to T1, there is this path through C1, and there is this path through C3. So it is 2. And of course, there are nodes that are not connected. So this is the problem. How do you go from here to there when the graphs are huge and still you want to do it in a main memory environment? Remember, we are still in the dungeon as part of a database system, gray pictures. Okay. For the mathematician there, let's say, just quickly, the graph is a bunch of nodes, a bunch of edges, and there is a label on every edge. We can have on nodes, but it's not important, and which is a function from the edges to a set of labels. But the key thing is, that's why I'm showing this, that there are two functions on labels, one on pairs of labels, where you take one label and then another, and you come up with a new label called con, for concatenation, and con can be any arbitrary function on pairs. And we have another one on ag, which is on subsets, on sets of labels. That's why it's an aggregation. And for all practical purposes, we assume that the aggregates that we're dealing with are either distributed or algebraic, which means that you can compute them incrementally. So this is what a label directed graph is. And what is the two-hop neighborhood? So you want to define the G2, which has most of the vertices, but not all, possibly all. The edges are the distance 2. And again, it's the labels I want to emphasize, that every edge in the two-hop graph its label is computed by con, applying the con on the two edges that make the path that gives you the distance of 2 between the nodes. And because you may have multiple such paths between two nodes, you saw an example, then you take and you aggregate all the labels that you get for these transitive edges. So this is the definition of more formal definition of the problem. So how do we compute this usually? So we have the graph G. Obviously, only nodes that have an outgoing edge will help will participate in computing G2. We want to go there. And only graphs that have incoming edge will participate on the target edge. So we can separate, we can think of having two subgraphs, the GS for source, where you have the S's that will be sources also in G2. You have the T's, which are the targets, and you have the C's, which are in the middle. And of course, some of the C's may also be S's, but in this example, I've simplified things without loss of generality. And usually we have the two functions, ag, applied on the cons of the labels. And usually it's done with two operators. You apply the con, you get an intermediate graph with possible multiple transitive edges between two nodes because of multiple paths. And then you apply the aggregation whenever is necessary, and you get this. This is what everyone is doing. Con and ag, possibly interleaved, we'll see. The thing is that how do you organize G or GS and GT for that matter? How do you store it in main memory so that you can speed up this processing? And the con wants it one way, the ag wants it another way. So these two operators antagonize each other in terms of what they want for performance. What is the right trade-off? What is the right deal? Let me quickly say that graphs in main memory are stored as adjacency lists. So you store all the nodes, and then in some order, arbitrary, doesn't matter. And then for every graph, you have another array where for the first node in the beginning, you have the targets of any edges that they have in this graph. And then when this one ends, the next one starts for its own target edges, targets of its edges, and so on. So it's two graphs. We talked about storing in main memory and processing in main memory. One of the beautiful views that you can have in this apartment of the entire building is that we have a memory hierarchy. Well, we have a memory hierarchy, and the graphs are stored here, but then you have caches, and you have the L3 cache, usually L2 cache, L1 cache. Sometimes you may even have 4 layers. The key thing is that as you go from main memory all the way to CPU core, you have smaller sizes, higher speeds, and more cost, of course, but the cost doesn't enter into the discussion today. So when you look something in main memory, if you find it in L1, it's ultra fast. If not, and you have a fault there, then you have to look into L2, otherwise in L3, worst case, you look into main memory. So when you have a working set of stuff that you are working on, you are dealing with, you're accessing, you want everything to be as high in this picture as possible, but it's not always. And it depends on how many data you are working on at any one moment. What is your working set? And if you take and look at the accesses Manos has done this for 2 CPUs. And you take an array of size, whatever the x-axis says, and then you do 100 million accesses on random accesses. This is the picture that you have depending on the size of the array. If it's very small, it doesn't really change. But then when it doesn't fit in L1 or L2, then it starts picking up, and then it kind of levels out, but still grows, and then so on and so forth. This is for random accesses. And the similar thing, different sizes of caches, that's why it's not the same. If it's sequential though, and you hit the same position, and then you go to the next one, and then you go to the next one, the size of the array doesn't matter because it's almost always there is prefetching, and so on and so forth. So when you try to process con and ag, how many random accesses you are doing and how many sequential accesses you are doing is very important. So let me show you a baseline algorithm. We assume that we'll take the GS graph with VS nodes and ES edges, and VT graph with and the GT graph likewise. We'll store them clustered on the sources both times. So this is the S nodes, and these are the C nodes. And then we'll try to synthesize them. So if you can follow, and as the graphs come out, as the end results come out, we have a buffer for all nodes of the graph because there can be potential targets of any source node where we can be calculating the end label. So Okay, come on. Okay, we start the loop. We loop through the nodes of VS. And for every node in VS, we go to the appropriate place in the edges, so the targets of these edges, which are stored here with a label. I'm not showing the label. This is sequential because this is sequential and this is sequential. So I don't bold anything here. And from here, we start for every C that we find here, which is again sequential. We need to find C wherever it is in the nodes of the other graph, and then find the start of its target edges in GT. And both of these are random because this is sorted based on whatever random order we've chosen. But here you don't have all the graphs, so it is in a random place and therefore in a random place here. That's why I have this bold. So these are expensive searches. The others are. And having done this, okay, and having done this, now we sort. We scan what is the targets of this node that was the target of C. We'll calculate the label of S. We are still on one S based on con. So we found one transitive edge. Then we find that node here in the buffer. That's another random. That's why I have it red. That's why this is bold in tbuffer. To update the label on tbuff, we can do it because we said it's distributed algebraic aggregation. And when this loop is done, and this for the targets here from one S until the next is done, we're still in one loop of S. We transfer tbuff. We have all the labels in G2 that start from S, and we are done. That's the algorithm. And up to here, when we calculate the con, is the operator con, and up to after here and until the end is the ag, each for one S. So you see, if we look now at the algorithm itself, these are the expensive operators. This is what we have to do something about to improve the performance of this algorithm. And if we see this and we take the graph that we have for our CPU that we use, and this one, these two operators are run once for every edge of GS. So we multiply all the points, and these are the two operating points for this algorithm, for these two expensive finds. One for the size of the nodes, one for the size of the edges of G. And this one is done once for every edge that is generated. So for every edge of the intermediate node of GX. So this is how many times we do the find. Fortunately, because we have tbuff, con and ag can be pipelined. We don't need to store these edges. So this is the processing cost of the algorithm. These are its random accesses, which are the expensive. These are this is a full algorithm. So what do we do? The name of the game of this work is we try to partition one graph into smaller pieces, trying to make the arrays that are that big, some of these arrays to make them smaller so that we'll bring them further down. And I'll describe one of the algorithms to get the feeling. The algorithm that let's look again at GS. Ignore this black line. I forgot to animate it. We have GS and GT. These three are the expensive ones. Let's try to partition GS. So how do we partition GS? We partition it on its target nodes, which are the source nodes here. So if we assume that we take, I'm not sure, why is this not advancing? I've been kind to it. Okay, let's assume that we partition the C nodes into three ones, these, and these three subsets, three partitions. And then, of course, together with them go in order their targets in GT. Now, according to this, we partition in these three partitions ES. So we have partitions now in S, and each node here has edges in the first partition, in the second partition, in the third partition. And we do the same algorithm again. As we start looping and we loop through this, when we finish looping, we will be done only one partition. So only we've calculated this. And then we loop again, then we do the second partition for all the S nodes, and so on and so forth. This is good because, as you can see, now the random accesses that are happening because of this list are in a smaller array. It's not the full array. It's a smaller array. And similarly here. So we win. The problem is now that when we are done with this, we haven't calculated everything for each S, but only the targets that arrive from one partition. So we cannot pipeline con and ag. This is the algorithm. Here is the partitioning step in different partitions of GS. These are becoming green, they are faster, but now we have to store all the intermediate graph and reread it again. There's no pipeline here now, it's store and forward. And what happens in this cost, the way we had them, these two improve. So these two move to the left, but we have now this cost, which didn't exist before. This one is not affected at all, it remains where it was. But now we have a cost, which is relatively random. I won't go into the details, which the more partitions we have, the higher it grows. So there is a trade-off. It improves, it doesn't improve, it depends on the data. Similar arguments, and I won't go into the details, exist for when we partition GT. In this case, we improve all random accesses, but unfortunately, we increase the number of times we have to do them. So although all three get better, those of con increase in numbers. So this whole graph diagram goes up, although the particular points move to the left. And we can also partition, we can do the whole thing and partition the result, the intermediate graph. And that's another option where it's again store and forward. We have to calculate it and then partition it. Here is the partition right at the beginning of AG. This improves this, but has the extra cost of storing and, GX and rereading it again. And this again, we have here improvement, but we have an increasing number of running because of these partitions. Do these graphs work? Quickly, some examples. When the number of the intermediate graph is, whether we construct it or not, is relatively small, we can afford to construct it, and partitioning GS is the winner. And various other measurements inside the core of the CPU is done, and you can see actual numbers now, where were the operating points in this actual experiment and where they went. You see, they fit, they take advantage of the caches. When it grows, and it is here, it's the example I show you has a ratio of 10. If it grows to 100, then this is no longer available, but we can still afford to create GX because it's done once per node. It's not for all S's. So we can afford to do partition X. And again, you see this improvement here. But when it's too much, so it is denser, the graph is denser, the two-hop neighborhood is 1,000 times greater than the original graph, then the pipeline is important. We can only have partitioning GT. So lots of more work to be done. but this is exciting for how to take advantage, and it's not just applicable for graphs, but this is what I wanted. And how can this help me? It can help me because recommendations can be done as graph explorations. And this is work by Marialena Kyriakidou, who has gotten her PhD, and now she's at Google, with your and our very own Georgia Kutrika. The main motivation is that the recommendation world is chaotic. Everyone is doing whatever they want, lots of techniques, each one as if it's something brand new. But it's not the case. Most recommendation approaches can be done, can be abstracted as a graph exploration problem. And by doing it in such a uniform model and a small number of abstractions, and I'll show them to you and they will be familiar now, you can capture many recommendation elements with one technique, explore connections, and facilitate the design of your algorithms and your processing a lot. So if you take a world, this is a model of rec graph, the way we call the system. You have a bunch of users, a bunch of restaurants and other businesses with characteristics, reviews that people have written, and then the schema of what everything is. What do you see? You see a graph. So how would you two like the restaurant T1? Well, we don't know. He or she has never been there. Or it's Johnny. So it is he. Has never been there. But there are other users that have been there. There are connections of this user with other users. So that we can find and we can predict directly. How? Through paths. Before, in the previous work, I showed you 2-hop paths. Now it is generalization. And by exactly the same argument, only that the paths can be longer than 2. You can find paths, labels of paths, in terms of what do I like, who do I trust, and so on and so forth. And then you can aggregate or fuse a variation. We can ignore this. And then we can predict how much you would like to go to V. 2 nodes, one a user, V is a. So exactly the techniques that we used before, generalized for arbitrary paths, can model recommendations. And this is just what does con mean? By now you should know. This is what arg mean. It's homogeneous labels, and fuse is for heterogeneous labels when between the same graphs, the same nodes. And whatever makes sense for your particular modeling of recommendations and the world you're trying to have recommendations on, you can choose particular functions. For arg, con, and fuse can be simple or arbitrary, and they have algebraic properties that you can take advantage of. And there is a query language, a logic-based query language that can capture such paths with aggregations, with cons and args and fuses. And we built a prototype like this on a graph-based system, Neo4j, one of the most, we don't like it, but it's one of the most popular ones. And what do you win? You win on expressivity. Many, we don't claim all, we haven't finished the work yet. Many can be expressed in this way. Usability improves and processing speed improves. Usability, see an example written in SQL, see how you can write it in the language by some paths, some graphs. Well, you say, okay, it's smaller but similar. Well, look at another one, tidal trust, an existing algorithm, very popular for trust-based recommendations. This is the algorithm. This is the same algorithm written through paths. Much more usable, the approach. And in processing, I won't go to the details. This is an algorithm, a plan that can be found out by the way a program written by an actual user in tests we've done with real users. But if you can take advantage of processing of algebraic properties that we have here, then you can use these properties. You can push aggregations further down and so on and so forth. and you can get an optimized plan. And here are some actual numbers. This is what Neo4j does. From left to right, in each case, you increase complexity and size. The first one is how RecGraph does it without optimizing it, and then with optimizing it. In all cases, the optimization that we can afford to do, it wins big time. That's the power of modeling recommender systems as graphs and taking the same path-based approach. And why did I want recommendations? The penthouse. Storytelling, story experiencing, a big team. There are others that I couldn't find pictures of. There are others that have contributed and are gone. But here is enough. Let me point out to your and our very own Maria Rusu and a whole bunch of amazing talent that we have in our team. What is the main purpose? Emotional engagement. How, when you interact with an environment with knowledge, you engage emotionally people. You build stories. You go into a museum and you don't go exhibit after exhibit and you just read a piece of paper or someone tells you a story and then you go to the next exhibit, which is completely disconnected. You have a thread of a story that the story leads you around the museum and around the exhibits. It can, whatever I say can be applied in many other environments. Museums have been our love, and this is our biggest experience. And in the History Museum of the University of Athens, we have developed such a story with professional story writers and directors and so on and so forth. If it is open, when it opens, you can go and download it from store and be done. So what should I study? The University of Athens Museum. And you had to have a digital story experience. In many other museums I'll mention, but you can get it from Google Play, and then you see the current museum building, which was the first building of the university from 37 that ECPA was established until 41. A bunch of amazing historical elements. How do you understand what studying at the time meant through a digital story experiencing in situ, in the museum, but also listening to the story? Amazing, we recommend this. What should I study? Google Play advertisement. In general, though, we want a visitor's experience to be as part of a thread, a story to be guiding you from one place to the other, to be looking at the exhibits and also looking, interacting with your tablet or mobile phone. Can also be having augmented reality, can have all this personalized, adaptive, based on what your interests are or how the story flows for you. This is a new form of art. It has many familiar stages that making a movie has. So preparing, collecting, having the idea, writing the script, staging it in the museum or whatever area you have. If it's virtual, then staging the virtual stage, making the production and then editing to have the post-production, the montage. And there are even more details in each part on that pieces that capture this model. So the key thing is to have that in an interactive way, as an experience, not just a narration, and to have it as much as possible to be adaptive. So let's assume that we have a simple story with horses. That's an example from the Acropolis Museum. You have horses, you have chariots, you have Persian horse. If someone, the system observes, and if he does this, then the person, again, what does it need to move down? Okay. If it skipped this, then the profile of this person is updated. If it completed it, again, positively it's updated. And if, but the narration may not be linear, may have intermediate branching points where after chariot horses, It can go to various chariot options, to go to Phaethon or chariots in war or chariots in life. And then it can ask the user, the visitor, what they want, or it can have, based on the profiles of users or characteristics, their age and so on, to choose. Again, this doesn't move. I don't know why. Okay. And the profiles are updated based on what is happening here. And then the decision can be made in a personalized way. You see, again, there is a graph. And the graph, this is the user model. And even the story was a graph. So we wanted recommendations modeled as graphs. All the lower levels of the house, of the apartment building, makes sense. Just to give you another flavor, in addition to recommendation personalization, we have worked and we are working on augmented and virtual reality to be able to see a white statue, for example, the colors that probably had. Also, we've done such work with stories, social individuals in many areas, in Çatalhöyük in Turkey, in the Stedelijk Museum in Amsterdam, the museum, of course, the Museum of Space in Toulouse, now with the Athens Ancient Agora, particular pieces there and stories in York Minster, where and also in Çatalhöyük, this is from there, where you can have experiences where you're exchanging actually physical objects, and you can interact people to people, people to bots. An amazing work that Maria Rusu and others have done on chatbot for this bot, the chatbot, and especially for children, but also for others. This work, if it decides to show up, it has personalization. Personalization is over here, or collaborative experiences, and storytelling. Where is it? Somewhere. But this has been exploding with this particular concept in mind. So many penthouses or new rooms in this penthouse are popping up with a sole goal to engage the person, and the evaluations are amazing on what works and what doesn't work, but getting people engaged with stories, with immersive or non-immersive stories is something else. And based on that, we are, in addition to research and technology, we are on our way to having a spin-off startup on our live learn, imagine, feel, because if you don't have this, you don't have a life. Having this, you have a life. So all these and many more are done in a team of 100 that I said. It's magic, very creative, knowledgeable, fun, great people from undergraduate students all the way to very senior professors emeriti. I'm really blessed and happy and lucky to be amongst all of them. We are not all work, we are having fun. This is from some beach party, and you can even recognize, if you try hard, some senior people here who teach you. Another party with the summer school, also many international people here. I won't point to people that we know. And also we have gatherings and retreats. We even play pool and stuff like that. So this is the team. These are my 2 email addresses. We may be around 100 by why not become 200. So if any of this or anything else that you see tickles you, we'll be glad to hear from you. Thank you very much. Let me stop sharing. And if I need to go back, I'll share again. Stop sharing. Okay.
Thank you so much for this excellent journey that spans from the basement to the penthouse and all the rooms in between. And we can now see that the basement is just as important as the penthouse. We tend to focus, or at least I tended to focus on the penthouse, but everything is interconnected, and that's what makes this so fascinating. We have some questions. I will start with the more, we have about 10 minutes, I think, for questions. So I will start with a couple questions that were included in the chat. About the two-hop neighborhood computation, a question from Yannis F. Asking whether it is applicable to non-directed acyclical graphs, that is, graphs with cycles.
Yes, it is. Then you have recursion on the cyclic graphs, and you can have bounded recursion. You can cut the cycles because in many cases, for your higher levels, the higher floors of this, cycles don't make sense, even if your data have cycles. Or it may be meaningful, and then the two hops have to be recursive. We haven't worked on, we have worked on paths longer than 2, on 3-hop or on n-hop. Preliminary results, we're not done with that with Manos. I'm not sure if Manos is in the audience. But when we are done with that, we'll look into recursion as well, and that will be tricky. But yes, it does make sense. How do you find the right trade-offs? It's another challenge.
Vasilis of Themiou asks about the many applications of your two-hop neighborhood computation work. So can you name a few that you may have tried or thought of? For example, could it be to speed up the training of graph neural networks?
There are many applications. Let's stick to 2 and not longer paths. Let's stick to 2. Wherever you have 2 antagonistic operators, even if they don't come from a graph, this is helpful. This is important. For example, as a database person, we have the join as our king or queen operator, and then often we have a group by, which is essentially an arc and a con and an arc, but beyond that. What do you do when you have 2 joins in a row? It's again three things that you're trying to have with 2 operators to join 3 things. How do you do that? The 2 are antagonistic. So that's a database application. And neural networks, we are trying to model them for the recommendation application. And we expect that it is doable, and we expect that the training of graph neural networks will be helped by techniques like the taking into account the cache hierarchy of the system. We haven't done it yet, to be for sure, but this is definitely one of the golden targets that we have. These are the 2 that I can think of. Of course, even in graph applications or recommendations as graphs, there are many that need some path requirements. I mean, all the shortest path and longest path and bill of materials and so on. It's transitive closures on DAGs. So the problem is there to be examined. Or friend of friends, it's a 2-hop. Similar items for recommendation is a 2-hop, and so on and so forth. So there are many higher level applications or lower level data processing applications where this appears to be applicable. Its effect, of course, we have to see based on details.
Any more questions from the audience? You can raise your hand. I think Yuli has raised her hand. So Yuli, would you like to ask your question?
Yeah, I decided to use this functionality and raise the hand so that other people also do this as we go on. First of all, thank you, Yannis, for the fantastic talk. It is an amazing view of a multi-story complex or several complexes actually. I would like to ask a question with respect to the last part, the storytelling. You showed us a very complex picture because it is a very complex problem. So just very quickly, maybe I'm trying to understand which part needs manual intervention. I imagine that writing the snippets or the text that connects to every, but then which parts are done or can be done automatically?
Let me draw a line and separate also in the architecture of that floor, the left side, which is authoring a story, and the right side, which is delivering a story, delivering an experience. The left part is creative, and we have built and are still developing tools to help the creators, to help the story writers, the paramithades, even the stagers and the directors to write a story that makes sense. Let me make a parenthesis. The biggest challenge in all of this is not technical. It's psychological, it's social. To write a story and the technology to deliver it in a way where the person, the user, the visitor will be engaged, will not interrupt the flow because something else happened or because they will be bored. Doing this, and in different environments, do you move a lot? Do you not move a lot? What kind of music you put in, and so on and so forth. It's completely artistic, and that's the biggest challenge. What we do in that left side and the right side is to provide the best possible tools to make the life easier. And we are in the process, after almost 10 years that we're working on this, we've been able to distill some tricks, so to speak, that of course Spielberg doesn't need them, but a young storyteller or story writer of this technology may be helped in creating meaningful stories and engaging stories for that. So this is the technology that we are putting in to help the users. Automatic story generation, I don't believe in. And even if some things arise, I mean, like paintings, some machines create nice paintings. With text and engagement, it's much more difficult. Even if it comes, we'll see. But currently, we are not thinking about that. The human intervention in the writing is definitely there. On the right side, it's up to the author again of the story whether they want to have the one who is experiencing the story participate in an interactive way or in a passive way, just follow and flow and so on, or do virtual reality or augmented reality or answer a question or play a game and so on and so forth. So it is up to the creator of the story whether the human will be part of the story. The technology is there to deliver it, and a lot of dirty things, the Wi-Fi and this and that. I mean, not exciting at all, but we've come along a lot, and people that know nothing about technology use our system and produce stories. And we had professionally one that you'll be paying money for. Currently, we have only one, but we are on the way to have some more. So our tools are quite advanced. But the main human intervention is by the creators.
Excellent question, Yuli, and obviously an excellent answer. The automatizing or automating the creative process is not possible, and we don't want to do it
We don't
either.
want that.
Exactly.
Yes.
But supporting the process is within our reach, I think, and that's what we are striving for. Any other questions or comments for Professor Ioannidis?
Don't. I mean, ask anything you want. It can be a simple question, or I don't know, but this or that. Doesn't really matter. This is great fun. And again, congratulations for the conceivers of this event. It's an excellent idea.
So I'd like to ask a more general question. Given that most attendees here are students who, during their studies, ideally get an idea of all of these levels. They get in touch with from the bottom to the top and from the top to the bottom. They span the whole polykatikia here. Which of the tasks?
Skyscraper, not
skyscraper. Yes, exactly. With very, very solid foundations.
Yes.
So which would you recommend, being a recommender system expert here, a recommendation system, as the most promising area or level research-wise for a data scientist to pursue, if you can recommend such a thing? I mean, would it be the lower levels or the algorithms that make the recommender systems more efficient or effective? Would it be the design of the applications, top levels? Does it depend on what would you, where would you say the future in data science lies?
Okay, I'll answer in two ways. The first answer is, you're asking me which of my children I love the most. Okay, and I love them all.
Provoking.
Okay. Second, I don't know if I would call the storytelling work data science. Everything else, but it includes data science. I mean, you need to monitor, you need the recommendation part is that. And therefore it is data science, has analytics, has
the applications at large, not just the storytelling.
Correct.
But the applications at large, and also issues such as challenging issues like the evaluating whether the recommendation system works. That's a very challenging issue. For example, isn't that also part of data science or the visualization?
Absolutely. Visualization is very important, and storytelling, the human-computer interaction aspects of it, whether it's some form of reality or not, or just the interaction and the even the surround sound that we may put to feel that is very important. We are very lucky. We live in an era of data science being very prominent, with other things, of course. Everything has too many challenges, and in my eyes, very exciting challenges, whatever you fancy. Some people like the dungeons, some people like the penthouse, and all of them are likable. I mean, since you see, I've lived in all, I am in all, I visit all, I love them all. All of them are really beautiful. And whatever do you fancy? I mean, when people come to work, to explore working for me for a thesis or other things, I ask them. I mean, I teach 3 data courses, and I ask them, let's say primarily 2, did you like design and use of database systems more, or did you like implementation of database systems? And independent of the grade that they got, and almost usually they like both, but almost all of them have a specific preference, and then I push them to the appropriate place. It's truly everywhere is exciting, and in many other things that I haven't touched because there was no time, or other things that our team doesn't work on. So whatever you fancy.
Great. and you have to fancy something so that you can do it well. You have
Absolutely.
to really love what you do.
Absolutely.
I think I will close. We will close
Yeah.
with a question by Maria Papadopouli. She has raised her hand, and this should be the last one, as we don't want to delay too much the rest of the workshop. Thank you, Maria.
Thank you. I'll be very brief. So it was a great talk. Thank you, Professor Ioannidis. I would like to ask a question related to the Human Brain project in which you are involved. And my question is threefold. The first part is, what is the most important scientific contribution of the project in your opinion? This is the first question. The second question is, what do you think is the most important challenge that you still need to tackle, to face? And a third, last question is, what you would be doing differently if you're starting the project again? Thank you.
Wow.
Sorry, maybe it was overwhelming. You can just answer the first one.
No, I'll answer all three. But I have a question to understand the context. Are these questions in relation to the neuroscience that the Human Brain Project is trying to serve, or is it in the context of the software infrastructure, the infrastructure, the research infrastructure that is being built, within which is also the federated learning, federated data, privacy preserving database system that we are involved? So is your question for neuroscience or for computer science?
Right.
Or
so,
for both?
Well, yeah, right. So it depends on the sub question. So the first question about the most important scientific result, I'm interested to have your opinion, regardless if it is neuroscience or computational. The second question about the challenge that you need to face is on computational aspect. And the third question, which is related to what the practical lessons, what you would do differently if you're starting the project from scratch. It is regardless if it is neuroscience or computational aspects.
Okay, great. By the way, when I accepted the invitation by the students, and I said, what am I going to talk about? Talking about the Human Brain Project, another related project that another part of our team is involved in, was an option. But in the end, I decided to go with this one. So what is the most important scientific achievement? I think technology there is to serve neuroscience. So I will focus on that. Technologically, there are advancements. Okay, neuroscience. I think the virtual brain is the most exciting in my eyes, the eyes of the computer scientists that just rub shoulders now with neuroscientists. I think the virtual brain is, and the Atlas, and these two. The virtual brain and the Atlas superimposed on that when this happens, I think will be a great leap forward. I mean, it will be discontinuity in terms of our ability to study the brain and then understand how it works. So I'm really looking forward for this to reach the point of maturity that they can be usable even in clinical practice and also in neuroscientific research for that. I mean, the brain, there is no single ailment of the brain that we know what to do with it. Yeah, there is no neurodegenerative disease that we have a cure for. And so it is a major frontier for medicine and so on. And I think the virtual brain and the Atlas are the most significant one. The neuromorphic computing and the neurorobotics, which come from the technological side, are exciting. but the jury is still out on whether they will achieve something big for that. So I would stick to TVB and the Atlas. Your second question was, what was?
May I interrupt?
Was related.
Yeah, I'll finish.
Yeah,
Maria.
sorry. The second question.
Brain is huge, and I think we don't want to distract.
Single liners. Single liners.
It was about the key challenges from the computational perspective.
Okay, the computational perspective. There are too many, but one that I'm working on with Minos Varoufalakis and team is on preserving the privacy of clinical data when you want to study them and come up with models of the brain.
Okay.
That's a big challenge. And what would I do different if I were to start the project again? I would, it is not scientific, it's not technological. I would involve more people, and in some cases other people, so that a lot of animosity that this project generated unfairly wouldn't have happened.
All right. Thank you very much.
We can talk more offline if you want on this.
Great, yeah, I would love to. Thank you.
And everyone else, feel free to look at the Human Brain Project, the website. It's a fascinating, obviously it's a fascinating topic and uncharted territory, and very difficult to really even start talking about it in the context of this or any other workshop, I think. So thank you very much, Professor Ioannidis. Thank you, everyone. This, I think, has been the best to start for this workshop, and we are, of course, a little bit off in terms of time, but we will go directly into the first session. I will hand it over to Dr. Koutrika to introduce, or the session chair. Yes, I'm sorry, Dimitrios Tsoumakos. So
thank you very much.
Thank you, everyone.
To all. It's been a great pleasure. Thank you.
Thank you, guys. Thank you for inviting me to participate. It's a great idea, and maybe we'll be using your expertise next year or collaborate in that. So let me just very quickly repeat the rules for the first batch of participants. So this is the first session, which is titled Data Storage and Representation. And I'm Dimitrios. I will be your session chair. So 10 minutes will be allocated to each of the participants / speakers for doing whatever they want, presenting their work to us. And then 5 minutes will be allocated on questions. I will do my best to scan, either raise the yellow hands or your questions on the chat. So without further ado, let's go right to our first speaker, which is Michalis Xydas. And the talk is DeepSqueeze, Deep Semantic Compression for Tabular Data. So Michalis.
Yeah, I'm here. Yeah.
Thank you.
So I will share my screen. I think that you can see my screen. Yeah.
Yes. Fantastic.
Great. So hello, everyone. I am Michalis Xydas, and I will be presenting DeepSqueeze, Semantic Compression for Tabular Data, a paper by these authors. So let's say that we have a really big CSV table, and we want to compress it. Well, the first thing that I would do would be to right-click on it and compress it as zip. But gzip, 7zip, etc. are general purpose tools. They can compress audio, images, etc. And maybe we can do something a little bit more use case specific. Well, we could use Parquet, which is a column-based approach, column-based compression algorithm that takes the first column of our table, compresses it, takes the second one, compresses it, etc. But we observe that our table has both row and column correlations. And Parquet makes the assumption that each column is independent of each other. So maybe we could somehow utilize these row and column correlations, and DeepSqueeze does exactly that. Okay, so we want to utilize correlations. In other words, we want to find a lower dimensional representation. What does that mean? Let's say that this is our original table. We can see that the first column is the same with the second one, while the third column is the same with the fourth one. So ideally, we would like to find the function f that takes as an input this table and outputs a lower dimensional representation that discards the second column and the fourth column. Now, we would also like this function f to be invertible, so as if we input the lower dimensional representations, we would get back the original table. Okay. So our function has to have two main characteristics. The first one is that it must take us from a large space, large dimension space n to a much smaller one m, and it must also be invertible. Now, finding f is difficult. It's an analytically interactable problem. So we'll do the best second thing that we can to approximate it. And we'll approximate it using a node encoder, a pretty straightforward neural network architecture. This architecture takes as an input the row of the table, encodes it into and compresses it into a lower dimensional representation or code, then passes it through the decoder, and ideally the output of the decoder should be exactly the same as the input. And we can think of it as the encoder part being the compression utility and the decoder part as the decompression utility. Now, DeepSqueeze, due to the continuous output of the neural networks, is a lossy compression algorithm. So we have to somehow enforce an error upper bound, ideally a user-defined error upper bound. So how can we do that? Well, let's say that this is our table. We'll first scale it to the range of 0 to 100. And we quantize it with a 10% error. 10% is user-defined, could be 1%, 5%, and it could be different for each column separately. Now it is a 10% error, so the quantization will map any value from 0 to 20 to 10, from 20 to 40 to 30, etc. Then we take each row of the table and we pass it through the encoder and store the lower dimensional representation. In our case, it's a one-dimensional representation, and store it into the code's data structure. Then we will take these codes and pass them through the decoder. And this way we'll create the decoded rows table. Why do we need that? Well, we will then compare the original quantized table with the decoded rows, and any cell that is not exactly the same will be kept into a separate data structure that will be stored in the final compressed file, and it will be retrieved at decompression. So we have some information about the compression and decompression utilities. I wrote the code, I did some experiments and got back some initial results, which are far away from the results reported in the paper. Well, and actually, my initial implementation was barely better than the baseline of Parquet and gzip, which are not lossy compressions. And I inspected a little bit the output files, and I saw that the failures data structure took a really big part of the final size, much bigger than I expected. So let's explain the problem in a bit more detail. Now, let's say that this is a row of our table. We encode it, we decode it, and get back these values. To calculate the failures data structure, we subtract from the original row the decoded one. Okay, and we get back these values. Well, we can see that the first and third row have a really small error, probably a non-significant error. So why do we care that we have these little insignificant, probably significant errors? Well, the failure data structure will be then compressed using Parquet. And if we have a huge number of really small errors, then Parquet will not be as effective. So an idea is to perform post-quantization. This is the equation of calculating the failures, the original equation of calculating the failures. And I do a really simple addition of adding a quantization step or you can think of it as binning, on the outputs of the decoder. Let's see it in an example. This is the same example. We encode the row, we decode it, and now we'll apply a quantization step. Again, as a result, we get back these values. And if we calculate the failures, we can see that we now have a lot of zeros, or in other words, a lot of unique failure values, making the parquet compression of the failures data structure much more effective. And here we can see some results. We are much better. This is the compression ratio, which is the final size of the file divided by the original size of the file. And we can see that we are close to the results reported on the paper. Still, we're not there. And there are some possible explanations about that, because they might have not used post-quantization, but something completely different that I wasn't able to infer from the paper. And also, we do not know their experiment settings. And since we are dealing with neural networks, the random weight initialization, and since we're dealing with small neural networks, the random weight initialization could have an impact. So that was a really quick overview of the paper, a quick overview of some of the things that I did in my implementation, and we'll continue with the demo. So I think the demo will be played by... Okay, yeah, perfect. So now I will present a quick demo of the DeepSqueeze compression utility of tabular data. For this demo, we will use the Intel Berkeley Research Lab sensor data. A table will consist of sensor measurements of 54 sensors in the research lab of Intel Berkeley. Okay, so I have already downloaded the dataset, the table, and you can see that it is 103 megabytes, which is pretty big. So let's compress it. First, we'll run the compression utility. As you can see, we take as an input the table, the file that we have downloaded, an output path, and an error, since this is a lossy compression. The error right now is 0.5%, not 50%, 0.5, so it is a really small margin of error. We have found the optimal parameters for batch size and code size in a relatively small search space. And we have achieved a compression ratio of 1.62%. Okay, let's see it created. And it is a 1.7 megabyte file, which is a really big difference considering that the original file was 103 megabytes. Okay, so now let's also decompress it. I have to mention that the compression utility and the decompression utility are completely independent. You do not need to have the compression utility in order to run the decompression. Okay, it has finished, and as we can see, we have created a new CSV file that is 126 megabytes, the decompressed file. Now let's compare the original file with the decompressed file to observe any mistakes, because since this is a lossy compression. On the left, it's the original table. We can see the original table, and on the right, the decompressed one. The columns are color-coded. And as you can see, in the first column, we have a 32 and a 32.1, which is pretty close, at 218 and a 224. They are pretty close, small margins of error. On the blue column, we have a 2, but here we have a 108 and a 11 and then 108. This seems like a big difference, but as you can see in the original file, the blue column takes really big values. So one could say that the difference between 3 and 180, it's relatively small for this specific column, since this column takes a large range of values. So this was the compression, this was the decompression, and we saw the original and decompressed file, and thank you for watching. So that was the demo. And if you have any questions, feel free to ask. Thank you.
Thank you, Michalis. We have about 3 or 4 minutes for questions for the speaker. So I see Antonis Papadakis and then Yuli.
No, I didn't want to ask a question. That was just a clapping hand.
Okay, then I go directly to Yuli.
Okay, the hands are confusing. Thank you, Mike, for the talk. Just a quick question. So, given that it is a lossy compression by design, what specific applications are we targeting with this compression? Because someone would say, I don't want to lose anything from my original data, and every time I compress and decompress, I maybe go away from what I had initially.
Yeah, that's a really good question. So it's meant for applications that have some error tolerance. For example, in the sensor data that I showed, we have measurements of temperature and things like that, humidity, voltage, that can maybe have some tolerance for small errors. Also, other applications are logs, statistics of logs, that we might be able to be a little bit more tolerant to the errors. So large-scale data sets that have some error tolerance, on them.
Thodoris, can you ask your question also?
Yes. So, Mike, congratulations for your work. What I would like to ask, because I didn't get it, I mean, did you finally manage to confirm somehow to replicate the results of the paper?
I was really close to the results. It is a bit weird because I didn't show all the experiments. In some experiments, the results that I got back were a little bit better than the ones reported in the paper. In some cases, like the data set I showed here, were a little bit worse. So maybe they have done something a little bit different in their implementation that I wasn't able to infer, or they did something a little bit different on how they performed the experiments. For example, I did the experiments 10 times and I averaged the compression ratio. They might have kept the best one or something different.
Okay, thanks.
There is a question by Chris Chapelas, if I pronounce it correctly. Increasing the dimension of the latent space, how much does it affect the decompression error? I guess that's the question.
Yeah, it probably depends on the data set. In our case, in around 3 or 4 data sets, 3 or 4 tables, it didn't affect a lot. It was in the range of 1 or 2 dimensions, or sometimes 3. But if you increase the dimension, you do not get back a better compression ratio. And also, that you are talking about the decompress error. This does not depend on the dimension of the latent space, but it depends on the quantization error that you set as a user. So I set 0.5% in my demo. That will be the maximum error that they will have as an output.
Okay, and the last one by Maria Papadopouli.
Yes, so actually I would like to ask you, what is the most important scientific or technical aspect that you learned in this paper that you want to share with us, that it was really important for you?
Yeah, that's a good question. So through the paper, I learned a lot about the autoencoders, and I guess that since I am in the deep learning field, getting a better understanding of what's the meaning of latent space, what latent space means, which sounds really overwhelming and complicated, but through the paper and by reading about autoencoders and other stuff like variational autoencoders, I got a really much better feeling about what latent space means, and that's much simpler than I was originally thought. And yeah, I would say this, my experience with the autoencoders.
Thank you.
Okay, let us thank Michalis. And we can go right into the next talk, which is by Christina Borovilou. And the title is Learning Multidimensional Indexes. So Christina, are you ready?
Yes.
Fantastic. The floor is yours for 10 minutes.
Okay. Hello, everyone. Today I will present Learning Multidimensional Indexes from MIT team. Indexing is a favored word for querying databases, and with time data become bigger and bigger. So we need fast tools to access them. Okay, this paper has come to give quick answers to questions containing many constraints. And let me introduce you Albert. Albert is a newbie librarian and he wants to make fast queries. Without indexing, he would do something like this in the library, but thanks God he discovered binary search. He is very happy and he accesses data very quickly. But then queries like this arrive, and two parameters are in the filtering session. So he's very angry because there are lines that he accesses that at the end they're not useful. So he wants to improve that. But the thing here is that a need or is a nice to have the query optimization? Okay, here we see that the iota bytes is in our door in 2030 will be here. So we can understand that is a technical demand. And one can say that secondary indexes can help, but disk is finite and maintenance is held by decision makers. So that is not the optimal solution. Okay, so Albert searched around his neighborhood and to find other solutions in multidimensional problems. He saws that AWS and Spark are using Z ordering to solve multidimensional queries. Vertica is using sort order over multiple columns, and IBM use R3. But he's not satisfied with these solutions, and he turns into data science solutions. So he introduced Flood. Flood is a multidimensional in-memory red optimized index, is a grid-based layout. And the key idea of introducing Flood is that it learns from queries and learns from data. What do we mean by that? Learns from data. One technique that Flood uses is that instead of uniformly divide the grid, as happens until now, into equidistant points, he adapts the grid to equally divided amount of data in its dimension. Another question that Flood is called to answer is how to form a layout. Here we can see that if you divide the layout sparely, you will have less subqueries to answer, but big overhead. While here you have a low overhead, but more queries to answer. So someone should answer that. And when we have infinite options and humans cannot answer that, machine learning appears. Okay, what are the parameters for the machine learning challenge? We give a data set, we give a workload of queries, and we find the layout that optimizes the time of the query. It is a need to use machine learning and not typical statistics because there are many interdependent variables with potentially non-linear relationships among them, and they cannot be defined analytically. Okay, in order to do so, machine learning flood, specifically generates random layouts, random ordering, and random number of columns, and then decides the best layout. During test, flood proved that outperforms in business data and in academic data as well. And apart from that, constitute a small index in memory. And if somebody would ask, okay, but what about the time that needs to learn? The metrics show that in 5 minutes it has managed to recover the loss of the learning. So to summarize, flood is a multidimensional in-memory red optimized index. It learns from data and learns from queries as well. And in any challenge, it has outperformed in any other existing index. Okay, the implementation we did here, as we didn't have the chance to have the code available, we tried to do the layout. As described in the paper, an optimal solution for the layout is to have ranges and nested sub-ranges on the dimensions that are not sorted, and to keep to left the last dimension to be sorted. So we have a layout something like this, that one dimension is not sorted but lives in some frontiers, and the other dimension live in that frontier. So the query can access in a more specific road and faster the information. Some future work that is to be done is to correlate the columns among the dataset to find skewness between the data. Maybe 2 queries are more efficient than 1, and to prioritize the famous attributes in the dataset. We can see more in the demo in a while for the implementation. Okay, hello everyone. Okay, now we will see the implementation that we did. From all the paper that is described is just the layout that we formed here. And here we can see a new tool, Excel. To the left side, we can see data as it is, and our implementation will try to structure them and to group them in, as we can see here. Okay, to do so, we will use Collab notebook. The thing that we need to do is to mount Google Drive in our notebook here, and from here we can take a path to load our data. So we run it. We can see a sample of our data with the student number, the graduation year, and the grade. Okay, next, a parameter that we need here is how spare our layout will be. It will be very dense, it will be something like that. But we want to be something like 3, as we can see in our data here. No, excuse me, here. That is divided by 3 in our example. So that we run it. Okay, we continue. Here we will give the columns that are participating in that grouping, the first and the second, the 0 and the 1 in Collab. And here we take the result, the desired result. So we try, let's go to see the grouping. Okay, here are the indexes that are mentioned. So it's 0 and 12 until 16. Copy it here. Then is 1 to 11, 17, 18. Okay, and the last is all this until 8 and 19. Okay, colors look good, so I will try to find out that is the structure over here. So with that example, we managed to order our data, and in the next episode we can do a search that is very fancy. Thank you very much.
Okay, so thank you, Christina. Are there any questions for Christina at this point? We have 4.5 minutes. I can take the first one maybe. Christina, thank you. I would like to ask the following question. I saw that in the experiments that you presented for the paper, they had a pretty long time span. So it was an hour and a half or something like that. And you mentioned that within 5 minutes, they were able to recover, to learn again what changed in the data. So can you tell us a little bit about what is the target applications, requirements in terms of accuracy and time span? So were there like thousands or millions of queries, and then some of them, only very few of them were inaccurate? Because that's a big time. So 5 minutes could be crucial for some applications or not so crucial for some others. Can you comment a little bit on that?
Okay, if I understood properly, we don't speak about the learning part, right? We speak about the application.
Yes, but the learning, as I saw, took about, as you said, it took less than 5 minutes to come back to high accuracy after, yeah. So what kind of application is the one that tolerate a 5 minute, or 3 minute gap in accuracy? That's my question.
That 5 minutes is not in every query. Whenever it is, you can run that thing at night, so that is the data are not in use for most of the businesses, and during the high time that are used, nobody will have a problem because they're already available.
Okay, but the learning occurs whenever data changes or whenever queries change, right?
No, in the paper they mentioned that they reevaluate the existing training model. They just do a reevaluation.
So they manually start the learning.
They don't retrain the model.
Any other questions for Christina? Yuli?
Yes, so during the presentation, you showed the formula. That was the formula that they tried to optimize during the learning process. So I was wondering, what are the factors that they take into account, the factors in the equation? There was a projection and 2 other things, if you can comment on that.
Yeah. Okay, projection is whenever the hypercubes that are formed, the layout, of course, is, we saw it in 2 dimensions, but it's a hypercube of dimensions. So whenever the hypercube finds the data, that is the weight, a percentage of how it was successful, and n is the data, the number of data that actually they were found. Refinement, it is only referring to ordered data. So we simply speak for the sort dimension, the unique one. And the scan is the time that takes the query to scan all over the target lines.
So we are past the 15-minute. Maybe Maria, Theodore, do you have a quick one? Maria Papadopouli.
Okay, I mean, let's continue.
Okay. Maria Papadopouli.
Okay. Sure. Yeah, I can raise a very quick question. So you presented the performance of different structures, some K-trees, hypercubes, etc. So database is not exactly my field. So I was wondering what exactly you learned. I mean, what was the key for you lesson looking at the performance from the perspective of these different databases approaches, data structure approaches?
Okay. My main gain from that was that actually applying a relation among the data, you can gain in storage, because if there is a logic between the data, you don't need to store them. So using intelligence, you can gain in storage.
Okay, anything a little bit more specific, if we have like a few seconds, something a little bit more specific towards the use, the specific technologies that have been included in the paper?
I happen to see many technologies from different papers, and I saw that even that there are deep neural network indexes that use simple models to simulate binary search orbit-trees that they treat them as models, even them. So I discovered that area of databases that a structure is not a structure, actually is a model. So you can see it in a wider sense.
Okay, all right, thank you.
Thank you.
Okay, let us thank Christina and move on with the next speaker, who is Aleksandros Kalimeris, and he's going to talk to us about optimal histograms with outliers.
Hello.
Alexandre.
Can you see my presentation?
Yes.
Okay, so hello everyone. My name is Aleksandros Kalimeris, and I will be presenting my project on the paper Optimal Histograms with Outliers by Rachel Behar and Sarah Cohen. We will start with a brief introduction, and then we'll discuss the goals and contributions of the paper, as well as the deletion approaches and strategies the authors propose for dealing with the outliers. Then we are going to see our implementation.
Alex, can you hear me?
Yes.
We don't see the full screen. We'll see the... so, yeah.
Yeah, okay.
I don't know why this happens.
Start the share screen after you enter the full screen.
Okay, sorry, let me do it again. Okay, is it okay now?
Now it's cool, yes.
Okay, and well, okay, we will show some implementation details and extensions we did, and finally we will go over some experimental results and conclusions. So summarizing big data sets is a process that lies within the heart of many applications, including databases. And a very intuitive and well-studied way of summarizing data is the creation of histograms. So a well-created constructed histogram can provide us with great insight about the distribution of the data. And there are many different kinds of histograms. However, we will focus on the V-optimal histograms today. So covering a data set with a histogram when we have a limited amount of buckets usually comes with an error. And in many cases, we can say that the elements that significantly increase the error can be viewed as outliers. So the focus of this paper is finding an optimal histogram with at most B buckets and the number K of outliers that we are allowed to leave out of the histogram so we can decrease the error. The main contributions of the authors are introduction of two intuitive notions of constructing optimal histograms with deletions, the consistent and arbitrary deletions, we will see later, the presentation of several algorithms, and extensive experimentations. So now the deletion approaches we talked about. The first one is the no deletions approach, that is the obvious one. Then the arbitrary deletions approach, shorthand ARB, that we create an optimal histogram and we are allowed to delete points from anywhere in our dataset. And the consistent deletions, CON in shorthand, where we create an optimal summary, allowing K deletions, but we are only allowed to delete from the left to the right edge of a bucket, and only if we can delete all the occurrences of that edge value. Next up, we're going to talk about the deletion strategies they propose. And there are three main strategies. The delete and summarize, where we first delete outlier with an outlier detection algorithm, and then we create the summary. The summarize and delete, when we first create the summary with no deletions, and then we go in its bucket and remove the elements that have the most error, add the most error. And finally, the main contribution of the paper, as I said, the delete while summarizing, where we delete elements while we're creating the summary, and they propose some dynamic programming algorithms to solve that problem. So for our implementation, we thoroughly read the paper and saw the algorithms that were proposed and implemented them in Python, following an object-oriented approach. We used NumPy and Pandas for numerical operations and data handling, respectively. And we should also mention that for the delete and summarize approach, in the paper they mention an outlier detection algorithm that we couldn't find an open source implementation. So we decided to use one open source one from scikit-learn, the local outlier factor, and it was quite well. It worked similar to the paper. So the algorithms presented in the paper were only shown how to calculate the error of the summaries. And while this is enough for benchmarking and comparing the algorithms, it is not of real practical use. If we want to use a histogram in real life and visualize it and stuff, we need the exact bucket ranges and the number of elements in each bucket. And to do that, we added some more matrices on the algorithm so we can keep track of those and be able to compute them as well. Now, let's take a look at some experimental results. Here is a figure from the paper where the authors ran its algorithm. Here are the shorthand names of each algorithm, and they ran them on two data sets, and they compared them to no deletion. Here is the ratio, meaning that we take the error of the algorithm and delete it by no deletion and see the result. So a lower ratio is better. And as we can see, the ARB algorithm performs the best, followed by SDARB, then by CON, which is in the middle ground, and SDCON. And finally, the delete and summarize approach, which shows little to no improvement. And the opposite trend we see in the algorithm runtime, where ARB, while it has a better error reduction, it is by far the slowest and it seems to not be usable in practice. We also recreated that experiment ourselves, and we see the same pattern. ARB was taking too long to actually execute, since we had implemented timeout in the algorithms. However, for the rest, the pattern is the same, apart from a little difference here, where delete and summarize gets a better error reduction than SDCon. However, this could be due to us using a different outlier detection algorithm that fits better the specific dataset. Next up, we tried these algorithms on a new dataset, which is about car listings in Belarus and the year that were produced. And again, we see the same trend and in a new dataset that was not used in the paper, meaning that probably the results of the paper generalize. Another question is if sampling can be used as a replacement for this outlier removal. And the authors of the paper proposed the following experiment, and we recreated it also, that we take a sample of the data, we create an optimal summary on the summary with no deletions on the sample, and then on the bucket resulting from this summary, we try to fit there the whole data set, and any point that doesn't fit in any bucket is considered a deletion. And then we run an optimal deletion algorithm, namely CON, with the same number of deletions. And as we can see, both in the results from the paper and in my experimentation, the sampling not only did not improve the error ratio, but it also increased it in many cases. Finally, since we used the interpreted language, that is Python, and it was slower than the one they used in the paper, which was Java, I thought of how we can maybe speed this up. And I thought of adding just-in-time compilation on the algorithms. And here is an example of the algorithm CON running with normal Python. And then when we added just-in-time compilation, and we can see a pretty significant speed up. So to conclude, the similarity of our results with ones we saw in the paper heavily reinforce the conclusions of the original conclusions of the authors. Deleting elements while constructing the summary seems to be a really effective way to reduce the error of a histogram. The algorithm CON provides the best trade-off between runtime and error. However, while these algorithms seem to work pretty well for the datasets we saw, they might degrade for extreme scale datasets. And a valid goal for the future would be the creation of new approximate algorithms to alleviate the previous problem. Thank you, and Ilias can play the demo. So now we are going to present a quick demonstration of our project. First, we are going to specify some parameters and which dataset we're going to use. Load the dataset. And now we're going to run two of the histogram algorithms, one with no deletions and one with deletions. And we will visualize the results on top of each other so we can see the difference. Okay, it should take a couple of seconds. And this is the result. The gray is the histogram with no deletions, and the blue one is the one with optimal deletions. And finally, let's show a really simple example step by step. First, we need to initialize two arrays, one with the values and one with the frequency of each value. Specify the number of buckets and the number of deletions. Then we can run the summarizing algorithm, which returns the error, the elapsed time, and the summary object. We can call the getBucketRanges method on the summary object, so we can get the left edges, the right edges of each bucket, and the number of elements inside each bucket. And finally, we can use the plot histogram function to visualize the result.
Okay, thank you, Aleksandros. We do have 4 minutes for questions. So I see Kostas Stefanidis.
Hello. Hi, thank you, Aleksandros. Very short question. Can you say a few more words about the method works actually? Delete while summarizing. Maybe it's more easy for us to follow the others, but maybe you can say a few words here about how it works.
Sorry, I did not hear the first part of the question. Can you repeat it?
To explain us a few more things about the method delete while summarizing.
Okay. Well, in that method, the main difference with summarize and then delete is that first we create an optimal summary without any deletions. So we already have the buckets, and then we go in each bucket and try to delete elements to reduce the error. While in that case, we are examining while running the algorithm and how we can actually split the data set into buckets. That is the main difference. That the buckets are not set from the beginning, and there are we like the algorithm constructs a matrix with many different cases of how we can split into buckets and how many deletions we can have from each bucket and so on. And from that bucket, we choose the case with the minimum. From that matrix, we choose the case with a minimal error.
Okay, thank you.
There is another question from Nikolaos Mirtakis.
Can you hear me?
Yes.
Okay, thank you, Aleksandros, for this presentation. And my question is regarding the outlier removal. So if I understand correctly, you first run an outlier algorithm like local outlier factor that, let's say, shows some scores. It scores every point, and the highest score, for instance, is the most anomalous. So you then remove these k points, let's say a predefined number from a user, or it's something different than that? How do you assess the abnormality and how it will affect the binning, essentially?
No, it's like you said, and that's why it doesn't work that well, because it does not take into account the binning, but only gives like a score to every point in the beginning and removes them, and then we create the histogram. So that was why that method did not work that well. It was kind of a baseline and a way for the authors to show why we need the algorithms they proposed.
And also what I didn't understand is that these histograms are constructed in a univariate manner, right? Like for every single feature of the dataset, or not?
Yes, they take into account only a single variable.
Yeah, and the problem is that, for instance, LOF is a multivariate algorithm. So the outliers that may exhibit are in a multivariate fashion and not in a univariate fashion that the histogram will consider. But there are other methods of histograms, like projection-based histograms, that you take a random projection of the data. So every single point is in a latent space, projected by, let's say, 5 or 6 features that may summarize another behavior of the point. And then it makes more sense to run LOF there because you use more features than just one to create a single histogram.
Yes, okay, I did not go...
But just food for thought, it's not...
algorithm I would choose. I thought that was like beyond the scope of my project. I just used that one, and since it had similar results with Yannis in the paper, I thought, okay, I will keep it. So...
Okay, thank you.
Let's thank Aleksandros and move on to the last speaker for this session, who is Giorgos Katsogiannis, who's going to talk to us about creating locally aligned embeddings for robust schema linking in text-to-SQL translation. So, Giorgos, you are ready, I see. The floor is yours.
Yes, thank you very much. Hello, everyone. Today I will be talking about a project based on an idea I had about creating embeddings specifically for the problem of schema linking. So first of all, what is text-to-SQL? So nowadays, business and most human operation is based on using data and taking advantage of data to make good decisions. But most data is stored in relational databases, which of course require the need of SQL to access it. So essentially they are making it inaccessible if a user does not have this technical knowledge and she does not know how to write SQL queries. So what if we could create an interface that would allow the user to query the database by just using their language, by writing questions in natural language? And actually, recently, we're seeing a lot of research on this subject, and thanks to two text-to-SQL datasets that have been published recently, this research is blooming, and we are seeing new systems every year and even every month, actually. But it still remains a very difficult problem, and we do not have a perfect solution yet. Now, what is schema linking that I will be focusing on in this project? Schema linking is the sub-problem of identifying which parts of the user's utterance, of the user's question, refer to which parts of the database or the table. So in this example, we can see that the word player is referring to the column player, the word number is referring to the column number, and the number 42 is referring to a value that is present inside the table. And we can also see that if we find these schema links, we have done a lot of work towards creating the correct SQL query for this question. And a lot of recent works on text-to-SQL identify this problem as a major challenge, but rarely do we see a system that focuses on solving this particular problem. So what I was hoping with this project is that by shedding light on this, maybe we could benefit many areas around this topic, including text-to-SQL. So what is my approach on this problem? Actually, it builds on a previous work that I studied for this class called Embeddings, and the idea here is to create word embedding representations from tables, from relational tables, and this is done by constructing a graph from the table and then deriving a text corpus and training an embedding algorithm, but we will see more about that in a moment. So I decided to take this approach of creating embeddings from a table, but we have another problem if we want to apply this to schema linking, is that the user is going to ask a question, and this question will have words that inevitably are not present in the table we are using. So for example, the word who, the word is, the word where's are not inside the table we're querying, so we will not have representations for these words. So my idea here, again, using a previous work that was published in 2018 in the MNLP, is that we can leverage pre-trained embeddings to get representations for these words that are not inside our table. But in order to use these effectively, we have to align the vector spaces of the new table embeddings that we're creating and the pre-trained embeddings that we're using for these words so that they mix correctly. So this is an overview of our approach. Essentially, we start with the table we're querying, and we use Embeddings to create a graph from this table and a text corpus from the graph. And due to time restraints, we cannot go in depth on this. But from this text corpus, we can use any word embedding algorithm we like to create table embeddings for our table. And we can also take pre-trained embeddings for representing the rest of the words, like we said, and align these two embeddings to create locally aligned embeddings that can be used for schema linking. And to test this approach, we also propose an automatic method for creating a dataset from the WikiSQL dataset, which is a text-to-SQL dataset that uses tables taken from Wikipedia, and it has natural language and SQL pairs on tables from Wikipedia. And the way we create the dataset is we take the user's question and the appropriate SQL, and for all the columns that are used in the select clause, and for all the columns that are used in the where clause, and for all the values that are used in the where clause, we try to find the most similar n-gram in the user question, and we take n-grams from length from 1 to 7, and we try to identify schema links in this way. And we also differentiate between partial and exact matches. So we have some statistics here, but the most important, I think, is the last row, that by using this method, we managed to cover 87% of the data set, and in the remaining 13%, we did not manage to find all the schema links, so we throw away these questions and we do not use them. So having created our locally aligned embeddings, and also having created this data set for testing, we propose an experiment. And for each schema link that we have discovered, if it refers to a column, we assign this word to the appropriate column. And if it refers to a value, we associate the word with the appropriate row. And then what we do is, for each word in the user's question, we calculate the cosine distance of the embeddings. And if we want to search for a column match, we calculate the distance from the words in the column name. And if we want to search for a match with a row, we calculate the distance from all the words in the values of this row. And then if the calculating distance is lower than a predefined threshold, we consider it a match. And we also calculate precision, recall, and F1 score for column and row matches. And we test and we compare aligned, locally aligned embeddings versus pre-trained embeddings using fast text and word2vec and multiple dimensions. And what we find is that pre-trained embeddings work much better when it comes to finding column matches, as you can see here by these very high scores from pre-trained embeddings. But when it comes to row matching, our aligned embeddings perform better than pre-trained. And as you can see, actually pre-trained embeddings do very poorly when it comes to row matching. So in conclusion, we have presented a way of creating table embeddings for the schema linking problem, and also an automatic dataset creation for testing this. However, there remains a lot of work to be done. We could propose more detailed experiments, use deep or machine learning, and also find better hyperparameters, because there's a lot of fine-tuning that can be done in all steps. And also generalizing to a complete relational database and not just a single table is always a very interesting problem and a very hard one. So thank you. We will see now a brief demo, and then we can take questions. So now let's take a look at schema linking embeddings in action. In our demo, the user can choose to load a table from the WikiSQL dataset. And in this case, we have loaded a table that has information about various episodes from a TV series, like their title, their director, original air date, and so on. So the user could ask a question, for example, tell me the production code of Vienna, which is the name of an episode. So as you see, the system correctly recognizes that the word code is referring to the column production code, and the word Vienna is referring to row number 5, which in fact contains information about the episode named Vienna. Let's try to load a different table. So here we have a table with information about basketball players, like their number, nationality, their school team, and so on. So the user here could ask, who played in Oregon? And in this case, you can see that the system correctly recognizes that the word Oregon is referring to row number 3, that has a player who actually played in Oregon. But it makes the mistake of deciding that the word in is referring to the column years in Toronto, probably because it contains the same word. So thank you for your attention, and feel free to ask any question you might have.
Okay, thank you, Giorgos. Questions for the speaker? I see Antonis Papadakis and then Vasilis Efthimiou.
Hello, congratulations for your talk. So I wanted to ask if you expect to have any collisions in your natural language questions, and if something could be done for that.
Can you explain what you mean by collision?
Yeah, maybe if there are some schema links coming out from different words that have different meaning, and then the link may refer to the same column, or if there will be a problem there.
I don't think there will be a problem from this system, because it can actually decide to match multiple words to the same column or to the same row. It's more of a question if it manages to find them, all of them, if there are more than one.
Yeah, I meant that if they had a different meaning and there were some problem with the matching, but okay, I got.
Yeah, the reason we're using word embeddings is that we want to also find different words that mean the same thing but are written differently. So that's what I was hoping to do. Okay, in the experiments it didn't go perfectly, but there's still room for improvement.
Congratulations, thanks.
Thank you.
Vasilis Efthimiou and then Theodore, who didn't get the last question. Okay.
Okay. Thank you for this presentation. Actually, I have also worked in this area, so I understand how difficult it is, and congratulations for this work. So I have many questions actually, but I will try to restrict just to the most important ones. So how complex are the queries that you can generate? For example, if my understanding is correct, it's more challenging to understand nesting or joins between two tables. Is that correct? Is this something you can do or trying to resolve?
Absolutely, it's a very, very challenging task, and right now we're not doing anything about that. We're using the WikiSQL dataset that has queries on single tables, so there's no joins, there's no nested queries, nothing like that, and it would be great to extend it, but we have many problems that arise. And first of all, how are we going to generate a dataset for that? Because we don't just have a select clause and a where clause, and we just take the columns and the values. We have nested queries with more columns, with more conditions. So it would be interesting, yes.
By the way, we have, if I may shamelessly advertise, we have a benchmark with nesting called FIBEN benchmark with dataset. And
I'm going to note that.
Okay. Yeah, it's very recent. So in the demo, you showed one example with query who played in Oregon, and then you showed one result, while there were two results at least visible in that table. So the current implementation is returning one answer, or it was just in this example?
Yeah, very good observation. No, it could return more than one. The case that was that it just didn't find the second one.
Was that because of the schema linking error in the in? You misunderstood
in
the
data
in.
set?
Yes.
It could be, now that you mention it, but it could also be that the system just didn't manage to find it.
Okay. May I ask a last question, or is there no?
I think
Okay.
that we can move on. Thank you,
Okay,
Vasily.
okay.
I'm
Thank
sorry
you.
about that.
No problem.
Thodori.
Strict chair. Okay, so congratulations, George, for your work. I noticed rather low values of precision and recall for the schema linking, right? So
Yes.
is this, I mean, what you're feeling, I mean, I'm sure that you've studied a lot of related work and state of the art out there. Is this the case for the current state of the art out there?
So right now, I don't think there is a work doing exactly this this problem. So even the dataset I just created it for testing it. And to be honest, there's still a lot of room for improvement. And as you saw, I didn't even have time to play with hyperparameters in the graph creation, in the word embedding algorithm, because word2vec and fast text take a lot of parameters for training the local table embeddings. So there's a lot of experimenting to be done and fine-tuning, and it is right now it is quite low. I agree, and I hope further work can improve that.
Okay, thanks.
Okay. Last question by Dimitris. I hope it's a quick one. Dimitris Kalou.
Hello, thank you. I hope the same as well. Thank you for the great presentation. The question I have is, if we have a very badly phrased question, will the system always return an answer, or can we get a no answer?
So the way I implemented it is that it will always return a column match, because we need to have at least something in the select clause. We need at least a column there. So it will return something even if the similarity is very low, but not for the rows, just for the columns.
Okay, thank you.
You're welcome.
So let's thank Giorgos and all the speakers. Great set. And back to the organizers.
Thank you, Dimitri. It has been a heavy program so far, but very interesting, very nice talks from all the presenters. But of course, as one of the organizers says, we are fashionably late. So we will have to make a very, let's say, small break. And let's resume in 10 minutes from now. Okay, so 12:30. So see you all in